Good morning, respected Chairperson, distinguished researchers, and fellow participants. My name is Muhammad Afif Rani, and today I will be presenting our work titled Room Temperature Vulcanized Silicone Rubber Based Nano and Microfiller Coatings for High Voltage Application, a mini review. This research was conducted together with my co-authors Muhammad Zulhilmi Mahmud and Muhammad Shafiq Afnan. This presentation will be broken into 7 parts. Introduction, research questions, literature review, methodology, discussion, analysis, and references. Modern infrastructure today depends heavily on reliable electrical power system transmissions. High voltage insulators play a crucial role in these systems by electrically isolating energized conductors from grounded structures, ensuring safe and stable transmission of electricity. However, insulators in outdoor environments are continuously exposed to electrical, environmental, and mechanical stresses. These stresses gradually degrade the physical, chemical, and physico-chemical properties of the insulator coatings. Currently, room temperature vulcanized silicone rubber, or RTV-SiR, is widely used as a protective coating for high voltage insulators. RTV-SiR is preferred because it offers several advantages, including high tensile strength, easy processing and curing, good mechanical durability, and excellent hydrophobic characteristics. These properties help prevent water film formation and reduce the risk of electrical leakage on insulated surfaces. Despite these advantages, severe environmental conditions can significantly reduce the performance of insulated coatings. In regions with high pollution levels such as coastal, industrial, or volcanic areas, contaminants accumulate on the insulated surfaces. This contamination can lead to loss of hydrophobicity, surface leakage currents, electrical flashover, mechanical degradation of the insulator. These failures may ultimately lead to power transmission interruptions. To overcome this issue, researchers have investigated the addition of fillers to RTV-SiR coatings. In particular, combining micro-based and nano-based fillers, such as hybrid fillers, has shown promising potential to improve the coating's physical, chemical, and physico-chemical properties. This study aims to address 2 main research questions. First, how do hybrid fillers influence the performance of high-voltage insulator coatings in terms of physical, chemical, and physico-chemical properties? And the second, to what extent can hybrid filler system enhance the durability and reliability of RTV-SiR coatings under harsh environmental conditions? By answering these questions, we aim to understand how hybrid fillers can improve the long-term performance of high-voltage insulation system. In this work, we conducted a mini review of previous studies that investigated RTV-SiR coatings containing nano and microfillers. These studies evaluated various test samples with different filler compositions, including combinations of silica and aluminum trihydrate. The objective of the review was to compare the performance and identify key trends and improvements reported in the literature. To simulate real surface conditions, most of the studies reviewed utilized accelerated aging tests. The aging tests were conducted using chambers designed based on STRI standards. These chambers replicate environmental stresses such as pollution, moisture, electrical stresses, and temperature variations. The accelerated aging parameters are commonly guided by Electrical Power Research Institute (EPRI) standards to replicate long-term outdoor exposure within a short time frame. 3 major parameters were analyzed in the literature. First is hydrophobicity. This property determines the ability of the coating to repel water and prevent the formation of conductive water films. Second, leakage current. The leakage current reflects the electrical performance of the insulator surface condition under contaminated conditions. And the third, chemical bond degradation. This is analyzed using Fourier transform infrared spectroscopy, or FTIR, to study changes in chemical bonds after aging. Together, these parameters provide insights into the physical, chemical, and physico-chemical stability of the coatings. Hydrophobicity was evaluated using water contact angle measurements. The surface condition was classified based on the STRI hydrophobicity classification, which ranges from HC1 to HC7. Lower HC values indicate strong hydrophobicity, while higher value indicates deterioration. High-resolution images of the water droplets on the coating surface were captured and the contact angle were measured to determine the hydrophobic behavior of the coating before and after aging. Leakage current was measured using a circuit configuration where the test sample was connected to a 1 mega-ohm resistor in series with the ground. The voltage drop across the resistor was measured using digital multimeter. Typical leakage current observed ranged between 1 microampere and 200 microamperes. Lower leakage current indicates better insulation performance and improved resistance against contamination. To analyze chemical degradation, Fourier transform infrared spectroscopy was used. FTIR identifies chemical bond structure based on absorbance peaks at specific wave numbers. By comparing the absorbance peaks before and after aging, researchers can determine the percentage loss of chemical bonds, which indicates the extent of material degradation. Based on the literature reviewed, several key trends were identified. Hybrid coatings containing nano and microfillers containing SiO2 or silica and alumina trihydrate demonstrated improved performance compared to pure silicone rubber coatings. These improvements were observed across multiple performance indicators. First, regarding hydrophobicity, hybrid coatings showed better hydrophobic recovery after aging compared to pure silicone rubber. Second, leakage current values were significantly lower to hybrid filler samples. This improvement is linked to the coating's ability to maintain surface hydrophobicity and high surface resistivity. Additionally, diffusion of low molecular weight silicon molecules towards the surface helps restore hydrophobicity after contamination. Finally, FTIR analysis showed lower chemical degradation in hybrid samples. This is partly due to the heat shielding and reinforcing effects of the fillers, which help protect the polydimethylsiloxane structure of the silicone rubber. Overall, hybrid filler systems is significantly enhances the physical, chemical, and physicochemical performance of high-voltage insulator coatings. In conclusion, hybrid nanofiller systems show strong potential for improving the durability and performance of RTV-SiR coatings used in high-voltage insulators. These coatings demonstrate improved hydrophobicity, reduced leakage current, and better chemical stability. As a result, hybrid fillers may help extend the service life of outdoor insulators, reduce maintenance costs, and improve reliability of power transmission systems. That is all for my presentation for today. Thank you very much for listening.